Hi everyone, welcome to section 8. Today we're talking about sampling and also the value of information. So let's jump right into the worksheet. The very first problem is on sampling from a Bayes net. We're given the following Bayes net and also these probability distributions over each of the variables in our Bayes net. In part A, we're given the following samples. And in part I, we assume that these samples came from performing prior sampling. What we want to do is calculate the sample estimate of P plus C. Before we jump into any kind of calculations, let's remind ourselves what is prior sampling. In prior sampling, it's the simplest possible form of sampling, where we essentially just sample the parents of each node in our Bayes net. Then we sample the children given the parents. And to compute the probability of any query variable Q given some evidence E, we essentially just tally up, count the number of samples that have both Q and E in them, and divide that by the number of samples that include E. So it's a simple counting procedure. So in this case, we're told that we're given already all these samples. So these samples came from doing this procedure of sampling the parents of a node and then sampling the children given its parents. And now what we want to do is calculate the sample estimate of P plus C. Well, in this case, we're trying to compute P of plus C, and there's no evidence. So there's no E involved here. And all that really means is that we're basically just going to be counting up the number of samples here that match plus C, and then divide them by the total number of samples that we took. So if we look here, which samples include plus C? It's this one, this one, this one, and then these two here. So in total, we have 5 samples that include plus C, and the total number of samples we took was 8. So our estimate of P of plus C given these samples is 5/8. Okay, next part says let's estimate plus C given plus A and minus D. We're going to clearly cross out the samples that would not be used when doing rejection sampling for this task. And then we want to write down the sample estimate of this quantity P of plus C given plus A and minus D. So let's remind ourselves what's rejection sampling. Rejection sampling is exactly like prior sampling, except we do this additional modification where we ignore all of the samples that are inconsistent with our evidence. What does that mean? It just means that if we get a sample, which in this case here, does not match the evidence plus A and minus D, we're not even going to include it in any of our counts. So if we look back at our samples here that we've been given, the very first thing we want to do is cross out those samples that are not consistent with our evidence. This means we want to look through each of these and ask, well, which of these don't actually include plus A and minus D? So the very first one includes plus A and minus D. That's great. Second one also includes plus A minus D, but this third one has a minus A, and this fourth one has a minus A. Both of those are not consistent with our evidence of plus A, so we're going to reject them. Then here we have plus A and minus D, so that's again not consistent with our evidence of minus D. This next sample here is consistent with our evidence. It has plus A and minus D. But now these last two are also inconsistent. So we're going to cross those out. So all we're left with are these 3 samples that are consistent with our evidence. And now to actually compute P of plus C given plus A and minus D, we're going to follow a really simple counting procedure just like we did before, where of these 3 samples that are left, we're going to count how many of them contain a plus C In this case, we have 2 samples that contain plus C, and divide that by the total number that we have here. So now that we've crossed out all of the samples that are not consistent with our evidence, let's go ahead and compute P of plus C given plus A and minus D in a very similar way to what we did in prior sampling, where basically we're just going to look at these remaining 3 samples and ask ourselves which of these have plus C appearing in them. That's going to be our numerator. So we're going to count, okay, there's 2 samples out of these 3 remaining samples that contain plus C. That's going to be our numerator. And then we're just going to divide that by the total number of samples we have here, which is just 3. All right. Next question asks us about likelihood weighting. So in likelihood weighting, let's remind ourselves really quickly how that works. Here we're going to fix our evidence variables. And then what we're going to do is we're going to weigh each sample according to the probability of the evidence given the evidence's parents. That's going to be what constitutes our weight W. So in this first problem, we want to, again, estimate another quantity. This time it's going to be P of minus A given plus B minus D. And we are told that these are the samples here that were obtained using likelihood weighting sampling. What we want to do now is fill in the weight of each sample in the corresponding row. So the first thing that we're going to do is we want to notice that we're going to weigh each sample by the probability of the evidence given the evidence's parents. So what's the evidence in this case? It's plus B and minus D. So here I'm just going to circle each of these. These are our evidence variables. And so to compute the probability of the evidence given the evidence's parents, what we're really going to do is leverage the structure of our Bayes net and then compute these respective probabilities. So here in the very first one, we're going to be computing probability of plus B given B's parent. And so in this case, we have that Bayes net, which has the structure A, B, C, D, this big causal chain. So B's parent is just A. So we have P of plus B given minus A times, and then we're going to also consider minus D and minus D's parents, which is C. So when we multiply these two together, we can query for these exact probability values here from our tables. So we're looking for plus B given minus A. So plus B is here and minus A is here. So we're going to write down 1/3 times, and then we're looking for minus D and plus C. So minus D and plus C is going to be 5/6. Moving along, we have next P of plus B given plus A times P of minus D given plus C. This is going to be 1/5 times 5/6. Then we have P of plus B given plus A times P of minus D given minus C, which is going to be 1/5 times 1/8. Then we finally end up with P of plus B given minus A times P of minus D given minus C. And this is going to be 1/3 times, and then we have 1/8. So we can just simplify these fractions really quickly here to get our final numbers. All right, So these are the corresponding weights for each of these samples. From the weighted samples in the previous question, we now want to actually estimate P of minus A given plus B and minus D. And yet again, we're going to be doing another counting procedure, but now we're going to be considering these weighted samples that we just looked at here and those corresponding probabilities. So what we're going to do now to compute the probability of minus A given plus B minus D is we're going to look at all the samples with minus A plus B and minus D. And then we're going to divide that by all of our samples above. And so what I mean here by all samples with minus A plus B minus D is we're just going to look at which of these samples contains exactly our query and our evidence, which is going to be, let's highlight these. It's going to be minus A plus B minus D. So it's this one. Minus A plus B and minus D. It's this one. These are the two samples that contain all these variables we're interested in. And we're going to take those weighted probabilities from here and sum them together as part of our numerator. So we're going to have 518 plus 124. And then we're just going to divide by all of the other summed probability values. Great. Last question, or second to last question here. Which query, P of D given A or P of A given D, is better suited for a likelihood weighting? Okay, so let's think about this. We have P of D given A, and then we also have P of A given D. If we remind ourselves how likelihood weighting works, we're going to fix our evidence. So what is our evidence here? So in this case, our evidence is A. In this case, our evidence is D. So we fix that, and now we're going to weigh each sample by the probability of that evidence given its parents. So if we look back at that Bayes-Net structure that was like this, I'm going to duplicate it over here. When we're looking at A as our evidence, then we're going to have to, for likelihood weighting, look at A's parents and compute W equal to probability of A given A's parents. Well, in this case, A doesn't have any parents, so no parents. While here, in this case with D, where D is our evidence, we have that C is actually a parent to D. So this is parent of D. And so when we think about which one of these two conditional distributions is better for likelihood weighting, you can think of it as, well, if we condition on A, then A actually doesn't have any parents. And so it's basically really easy to compute the weight, because it essentially just boils down to computing P of A, because the weight equals to P of A given A's parents, but A doesn't have any parents, so it'll just be P of A. While here, the weight would be equal to P of D given D's parents, which would equal P of D given C. And so in this case, P of D given A is preferred because it's just simpler, and we can essentially only consider, we're only conditioning on evidence that's upstream from our query variable, and it essentially makes our computation simpler. All right, last question from this problem number 1. We're now looking at Gibbs sampling. So recall that during Gibbs sampling, samples are generated through an iterative process. Let's quickly remind ourselves of how Gibbs sampling works. So what we're doing in Gibbs sampling is we fix our evidence. Then we're going to initialize all other variables randomly. And we're going to repeat in a loop, choosing a non-evidence variable x, and then resampling x from the probability of x given its Markov blanket. As a quick reminder of what the Markov blanket of a random variable x is, the Markov blanket consists of the parents, children, and the parents of the children. Here's a little visual description of what the Markov blanket is for x, which you should have seen from the prior two discussion sections. Two important notes about Gibbs sampling. First, because we fix the evidence, we never change it. That's one important property. Another thing is that in this iterative process, in this repetition of this iterative loop, we're going to update at most one non-evidence variable per iteration, because here we choose one non-evidence variable x and then resample. These are two important things to keep in mind. So this problem now says that assume the only evidence that's available is plus A. Clearly fill in the circles of the sequences below that could have been generated by Gibbs sampling. Okay, first thing we should sanity check is in Gibbs sampling, we are told that we have this evidence plus A. This is our evidence. And we know that Gibbs sampling never changes the evidence. So if we look at any of these four sequences and we see that the value of plus A has changed, immediately we know this couldn't have come from Gibbs sampling. And turns out that actually sequence 2 violates this. Right here in this third iteration of the procedure, we see that A suddenly goes from being plus A to minus A. And so this sequence could not be generated by Gibbs sampling because it changes evidence. So not from Gibbs. Okay, the second property that's important about Gibbs sampling is that it updates at most one non-evidence variable per iteration. So let's look at each of these and see whether or not that holds for each of these iterations. So in sequence 1, at the very first time here, nothing has changed, and that's okay, because in Gibbs sampling, at most 1 will change. But then we see between iteration 2 and 3, minus C becomes plus C. But that's okay. Again, we update at most one non-evidence variable per iteration. So everything looks good here in sequence number 1. This could have been generated via Gibbs sampling. What about sequence number 3? In sequence 3, we change from plus D to minus D between iterations 1 and 2. And then we change from minus B to plus B in iterations 2 to 3. But again, we're just changing one non-evidence variable per iteration. So everything looks good here too. Finally, in sequence number 4, what's going on here? We see that we change from plus D to minus D between iterations 1 and 2. But now between iterations 2 and 3, we change from minus B to plus B and from minus D back to plus D. So these are two changes of non-evidence variables. So this, again, is violating this property of Gibbs sampling. So this could not be generated from Gibbs sampling. Cool. So that's that for problem number 1. Let's take a look now at decision networks and the value of perfect information. So here we're told that a used car buyer can decide to carry out various tests with various costs. Depending on the outcomes of the tests, they'll decide whether or not to buy that car. We're going to assume that the buyer is deciding whether to buy a car C, and that there is time to carry out at most one test, which costs $50 and can help figure out the quality of the car. A car can be in good shape. So we're going to represent that by the random variable Q taking on the value plus Q, or in bad quality, which will be represented as not Q. And the test might help to indicate what shape the car is in. There are only two possible outcomes for the test. Either it's pass or it's fail. And the car costs $1,500 and its market value is $2,000 if it's in good shape. If not, it's going to cost $700 in repairs to make it be in good shape. The buyer's estimate is that C has a 70% chance of being in good shape, and the decision network is shown below. Let's quickly remind ourselves what this decision network represents. Square or rectangle nodes represent actions. So this is representing whether or not the buyer should buy the car. They can take that action. These diamond nodes represent utility. So how much value the buyer gets from this particular car purchase. And then these circle nodes are chance nodes, which represent, in this case, the probability of the test passing or failing, and also the probability of the car being in good or bad shape. Okay, we want to calculate the expected net gain from buying the car C given no test. So to calculate this expected net gain, we can think of this in the context of the languages of decision networks as computing the expected utility of buying a car given no test. So it's the expected utility of taking the action A, which is representing buy, given that you decided to not take any test. So here is a quick general formula for how to compute the expected utility of an action little a given evidence little e, where you basically go through and you sum over all of the chance nodes, which are these big x1 to xn's, conditioned on the evidence. You multiply the probability of these chance nodes given the evidence times the utility that you get from taking action A, and all of these chance nodes taking on the values x1 to xn. So we're going to apply this formula for the specific part of our problem here. So we're trying to compute the expected utility of our action equaling buy. And we're not given any evidence because we're not given any test results. So we're just computing the expected utility of buy. So that means that anywhere we're seeing this big E equals E, we're not going to be conditioning on anything. So in this case, we're going to sum over Q, which is this chance node here that represents whether or not the car is in good shape. And we're going to compute the probability of Q, big Q, the quality of our car, equaling a particular value, little q, times the utility of taking the action buy, and q being a particular value of the car's quality. So we know that q can take on plus q and not q, which represents good and bad quality. So we can expand this out by writing out p of plus q times the utility of buy and good quality, plus the probability of not q times the utility of buying when it's not in good quality. Okay, what are each of these values here? Well, we're told that we have a 70% chance of the car being in good shape. That means that the probability of plus Q, or the car being in good shape, is 0.7. And then what's the utility of choosing to buy when the car is in good quality? Well, to figure that out, what we are going to do is we can see here that the car costs $1,500, but its market value is $2,000. if it's in good shape. So assuming here that we're plugging in that the car is in good shape plus Q, the total utility that the person's going to get here from choosing to buy is going to be the total market value minus the price that they purchased it for. What about the probability of the car not being in good shape? It's just going to be 1 minus the probability of the car being in good shape. So that's just going to be 0.3. And then what about the utility of buying when the car is not in good shape? Well, in this case, we know that the car still has a market value of $2,000 if it's in good shape. But we know that to get it into good shape, if it's not in good shape, we need to spend $700 in repairs. So that means that we're going to have to spend $1,500 and an additional $700 to get the car into good shape so we can sell it for that market value of $2,000. And so now if we consider these in total, what we're going to finally get is a total expected utility of 290. Note here that we actually lose money in this case here if we decide to buy and the car is not in good quality, because we'll be essentially losing $200, while in this case we'll be actually making $500. Cool. Tests can be described by the probability that the car will pass or fail a test given that the car is in good or bad shape. We have the following information. The probability of passing given that the car is in good shape is 0.9, and the probability of passing given that the car is in bad shape is 0.2. We want to now calculate the probability that the car will pass or fail its test, and then we want to compute the probability that it's in good or bad shape given each possible test outcome. So let's break this down. We want to first compute the probability that the car will pass its test. So this is P of T equals pass. Well, since we're given the probability of T equals pass conditioned on the quality of the car, what we can essentially do is use our probability knowledge to marginalize over the possible values of Q, and looking at the probability of T equals pass conditioned on this value of our car's quality times the probability that our car is actually of that quality. And we have all of these entities already, all these quantities. So this is just going to equal to P of T equals pass given plus Q times P of plus Q plus P of T equals pass given not Q times P of not Q. All right, we were given in this problem that this probability is 0.9. From above, we already know that this probability of the car being in good shape is 0.7. From above, we have that the probability of passing, given that the car is not in good shape, is 0.2. And from above, we also know that the probability of the car not being in good shape is 0.3. So in total, we have 0.69 as the probability of the car passing a test. What about P of T equals fail? Well, here we can use our total law of probability and understand that because T can only take on two values and it has to be a valid probability distribution, we can just compute 1 minus P of T equals pass to get the probability of T equals fail. So this is just going to be 1 minus 0.69, which equals 0.31. Let's circle this guy too over here. All right. So we've computed the probability that the car will pass or fail its test. Now let's compute the probability that it is in good or bad shape given each possible test outcome. So in mathematics, what that really means is we're looking for P of Q equaling plus Q, which is good shape, given that it, for example, passed the test. And we're looking for P of Q equals plus Q given T equals fail. These are two quantities which represent the probability that the car is in good shape given each possible test outcome. To compute these, we can use, again, our knowledge about probability and Bayes' rule to first write out the joint distribution of plus Q and pass divided by P of pass. Then we can split up this joint probability on top into P of pass given plus Q times P of plus Q divided by P of pass. And lucky for us, once again, we have access to all of these quantities. So P of pass given plus Q has been given to us here. It's 0.9. P of plus Q is 0.7. And P of pass, well, we already computed that. We just computed that right here. It's equal to 0.69. And so finally, this total probability here equals 21 over 23. What about this other probability that we're interested in? We're going to apply the same procedure. We're interested in P of plus Q and fail divided by P of fail. We can divide this once again into two individual probabilities. The first is the P of fail given plus Q times P of plus Q divided by P of fail. All of these we have access to again from the prior problems. We have 0.31 as the probability of fail, 0.7 as the probability of the car being in good shape, and the probability of fail given plus Q is going to be 0.1. So overall here we have 7 over 31. Great. Okay, we want to now calculate the optimal decision given either a pass or a fail, and then also the expected utility of these optimal actions. So as soon as we hear the words optimal decision, and when we have sort of uncertainty about how much utility I'm going to get, what this makes me think about is computing a maximum expected utility. So in the problems above, we were computing the expected utilities here of taking a specific action A and having evidence E. But now if I'm trying to make an optimal decision, what I really want to do is I want to maximize my expected utility. I want to choose an A such that I maximize my overall expected utility. And so that's basically what we're going to be doing in this part of our problem. We're going to be computing the maximum expected utility given the evidence of passing or failing. And we want to choose this action which leads to this max. So let's go ahead and do that. So let's write out some of these expected utilities that we have here. So the expected utility of choosing the action to buy, given that I passed, is the probability of plus Q given T equals pass times the utility of plus Q and buying plus P of the car not being high quality given that I passed the test times the utility of the car not being in good quality and I also buy. So this equation is just exactly that same equation from up here that we used in part A, but now I actually have evidence, which is information about whether or not I passed or failed the test. And so that's going to be involved here in this computation of this initial probability. All right. If we plug in all these probability values here, we have most of them already on hand. We already know that the utility of buying the car when it's in good quality gives us a total net gain of $500. If we buy the car when it's not in good quality, we lose $200. And then the probability of the car being in good shape given that it passed, we computed above. That's going to be 0.91, and this is going to be 0.09. Let me change these colors for consistency. All right, so overall, what is this total here? It's going to be approximately equal to 37, excuse me. Okay, what about the alternative outcome for my test? What is the expected utility of buying given that t equals fail? So it's going to be exactly the same equation, except we're just going to be plugging in t equals fail everywhere where we used to have t equals pass. So we have the second probability being P of not Q given t equals fail, utility of not good quality, and I buy. All right, well, we have, again, a lot of these quantities on hand. The utilities haven't changed here. What has changed, though, is the probability of the car being in good shape, given that it's failing. This is 0.22, again, from the prior part of our problem. And this one is going to be 0.78. So overall here, we're getting minus 46 expected utility. Finally, what about if I'm not buying? So here we just computed the expected utility for the action buy, but the other option is to not buy. Well, the expected utility of not buying given t equals fail, and the expected utility of not buying given t equals pass are the same. They're both 0. I don't lose anything, I don't make anything. So now what we're trying to do is figure out the optimal decision given either a pass or fail. So now what we want to do is we want to compute opt decision, let's say given that t equals pass. So what this will equal is we're going to take the argmax. So we want to find the action which maximizes the expected utility of taking that action given that t equals pass. Okay, well, we have computed these values. So here we're taking the argmax over actions of the expected utility of buying given pass and the expected utility of not buying given a pass. Well, not buying gives me an expected utility of 0, but buying if the car is passing gives me a utility of 437. So the best thing for me to do here, the action which maximizes my expected utility, is going to be to buy. And this gives me an expected utility of 434. What about the alternative? So I'm spilling in here to the other part of the problem, but let's just take up some space here. So we now want to compute opt decision given t equals fail. Well, again, this is going to be argmax over the actions of the expected utility given that I'm failing the test. This is going to just be the argmax over the actions of the expected utility of taking an action given, the expected utility of buying given fail, and the expected utility of not buying given fail. We know that not buying gives us an expected utility of 0, but even worse, if I do buy and my car is failing the test, I'm going to get an expected utility of minus 46. So the max between these two will tell me, hey, in this case, you should not buy. And this will give you an expected utility of 0, which is better than minus 46. Awesome. Let's look at the very last question now. All right. The very last question asks us about the value of perfect information of the test. Should the buyer pay for a test? So let's remind ourselves of what is the value of perfect information. Intuitively, the value of perfect information is how much the agent's maximum expected utility is expected to increase if they observe any new evidence. So mathematically, what that means is here, this E prime is this new evidence that we're observing. And then this E equals little e is our old evidence. And the value of perfect information is going to be computed as the difference of the maximum expected utility from both the new and the old evidence minus just the old evidence. This component here, this maximum expected utility of both the new and the old evidence, is just computed as an expectation over the new evidence, where you say, give me the probability of the new evidence given the old evidence times the maximum expected utility of the old evidence and the specific value of new evidence. And we have to do this expectation because we don't actually know what this new evidence is going to be. We don't actually know which value of E prime to plug in. So we take an expectation over all these values of E prime to approximate that, or to get an estimate of this maximum expected utility given some new evidence E prime. So in our problem, we want to compute the value of perfect information of the test. So we want to compute value of perfect information of the test. And here we're really not given any old evidence. So I'm going to denote here sort of no evidence, or let's actually do this in two steps. I want to compute the value of perfect information of a test, and I'm going to write this equivalently as the value of perfect information of t given this empty set symbol here, which I'm just going to call no evidence. No old evidence. Applying our formula here, we're going to be computing the maximum expected utility of knowing nothing and our new evidence about the test minus the maximum expected utility of knowing nothing. No old evidence. Let's expand out this first maximum expected utility via this equation here. So we're going to sum over all possible outcomes of our test and compute P of t equals t, given no old information, no old evidence, times the maximum expected utility of that test outcome and no evidence. Then we're going to take that whole quantity and we're going to subtract from it the maximum expected utility of no old evidence. All right, well, lucky for us, we know all these outcomes that could possibly happen from our test. So we have P of T equals pass given no old evidence times maximum expected utility of T equals pass and no old evidence plus P of T equals fail given no old evidence times maximum expected utility of T equals fail and no additional evidence minus maximum expected utility of no evidence. Probability of passing given no old evidence was something we actually computed earlier. So here, this is just the raw probability of passing. And that was 0.69. We also computed just the probability of failing given no other evidence, and that was 0.31. So we're going to plug those values in here. So this is going to be 0.69, 0.31. And then what's the expected utility, the maximum expected utility of passing or failing? Well, that's something we also computed. So here, we know that the maximum expected utility, if the car is actually passing, is to get $437. So if the car is actually passing, we want to get that maximum expected utility of $437. What about the maximum expected utility if the car is failing? In this case, it's best for us not to buy, not to do anything. And in this case, 0 is the maximum that we can get. Finally, what about this maximum expected utility of gaining value when we don't know anything? This component is something we actually computed way back in the earlier part of the problem. So at the very beginning of this problem, remember, we calculated the expected gain from buying the car given no test. And so this expected utility is exactly capturing this quantity that we care about, which is how much value do we get if we just buy the car and we have no information about our test. And that was $290. So here, this was 290 from part A, where we computed expected gain from buying car without evidence about test. All right, if we plug in all these numbers, multiply them out, we'll get a total of 11.53. So we were doing all these calculations to answer the question, should the buyer pay for a test? And basically, since it costs $50 to do a test that was originally stated in our problem, we shouldn't pay for it. Because we'll only get a gain of $11.53 when it's actually costing us $50 to do that test. But the amount of expected utility increase is only 11.53, which makes it not worth the extra money that we would spend on actually doing the test and actually getting that evidence. And with that, we're at the end of section 8. Thank you so much for joining.